So the first thing, I tend to just talk about aims and objectives and things rather than not read them out. So the first thing we're going to do is have a look at some of the workings of a magnetic compass and magnetism and how it all works. And it's a little bit tricky to turn onto a compass heading because there's a whole lot of errors we have to compensate for, and we have to understand them and learn how to compensate. Because ultimately, we might need to use our compass if our flash instruments should fall over. Our compass is the last resort. But also importantly, you'll need to demonstrate that you can do this if you were to pass your flight test. I actually had a student once that had a bit of a brain fart during his PPL and could not do a compass turn to save himself. First time ever, he was really good at them. Failed his PPL on compass turns. So don't take them lightly. So at this point I'll probably ask the class, or this, I tend to think about one-on-one with a briefing, whereas I think you guys think more along the lines of mass brief, don't you? So I generally just pitch it at one blogs, not a class. It's just what I revert to because that's what I used to do before I came here. Oh, here he is. Yeah, at this point I might ask the class, what's the most likely way of losing all our flash means of indicating heading and turning that we've got on the PFD and stuff? What's the most likely thing that could go wrong and prevent us being able to use that? And hopefully some bright student or blog says, oh, you have a power failure. So we're looking at a picture of our compass. And what does it read, I might ask? And blogs will say, oh, and you can critique it from there. What's that, that thing beside it, that little bit of paper that says steer? Let's see if they register what that is, because they should have actually been looking at it on their pre-flight. That'd be a good thing to just mention on the way through this. And then we're going to talk about Earth's magnetic field. And there's some really good speaker notes here. Inside the Earth is a giant bar magnet extending out from each end of the giant bar, blah, blah, blah. So you guys can work your way through this easy enough, I think. We can talk about how the poles are the axis on which the Earth rotates, and how the magnetic poles are slightly different. Geographic poles, magnetic poles, and flux lines. So I think you guys can mull your way through this one. There's some really good transitions, flux lines, and then the compass on the aeroplane is also a magnet, and it's going to want to line up with those flux lines. That's how we navigate. And then we need to talk about dip. So there's our flux lines again. So how would you describe the flux line at the equator? How's it orientated? Perpendicular or something else? It starts with P, parallel. imagine the compass sits nicely parallel with the Earth's surface, or tangent to the Earth's surface at the equator. Is that going to be the case as we move up or down in latitudes? No. So the compass is going to want to line up with those flux lines. It's not going to want to sit level. And this tendency is known as dip angle. So we work our way through that slowly. And blogs will be able to tell you what the angle is going to be at the magnetic pole when you ask. Another good question. Do you reckon the compass is going to work at the South Pole, or very close to it? Are you going to be able to use the compass to navigate? No. And you could either ask it or just state it. Angle of dip in New Zealand. So on the left there we've got the equator, no problem at all, but the tendency of our compass, or our magnet in our compass, to dip down by 60 degrees at our latitudes. So that's only leaving that horizontal component that's of any use. But it's still going to work quite well. But we need to correct for it. We want it parallel to that tangent to the Earth. So, it's a bit of a seesaw thing. On the left, our compass lining up with the flux lines. Now, if we suspend the compass like a pendulum, that'll happen. Another thing we could do, you remember when you were kids sitting on the seesaw, what happened if your big brother or your little sister hopped on the other end? So we could offset the C of G, if you like. But you'll notice in the picture there's still a little bit of residual dip. It's nearly parallel. So there's the two methods, suspending it, how do you say that, penduously, or weighting the magnet, putting some weight, big fat big brother on one end. So at the end of the day we're going to have a couple of degrees residual dip, which is negligible. I'd actually like to have a picture of some of the older compasses. Have you seen them in vintage aircraft? Big ones like that between the legs? Yeah, they're pretty cool. Right, so let's look at the construction of the compass. So far this brief's quite good. I kind of feel like I could go through it cold turkey with the class just about. With the speaker that was on the presenter view. So there's our compass. So we've got basically a magnet sitting in the flux lines. And north is up the top. So the north end of the magnet, or the compass, is up the top in the picture there. Now what's the next transition? Well, that's what you'd be looking at in one of the old-fashioned compasses, because you'd be looking down on it. But we can only see a little bit of our compass. So notice we'll swap it around. So even though north is at the top, we have north, oops, what happened there?
It's back on.
Hey?
We came back on.
Yeah, I think I just kicked it down there. Yeah, so north is north, but this is how our compass is arranged because, let's look at the next picture, we're not looking down on the compass. You might need a bit of a pointer for this one. Do we have a pointy thing? This is what our compass looks like, eh? It's called a direct reading compass. So there's a big compass in a little aeroplane. The pilot sits here and looks at that view, and he sees north when he is flying north because the compass north is the way we're going. So spend some time making sure student understands the direct reading compass principle. And it becomes important later on because they need to get their head around the compass and the pilot and the aeroplane turn around the compass. And there's good animations for that, I think, from memory. Oh, it might be on here. I'm just going to push the button. I think there's hopefully an animation. There we go. As we turn right, you can see numbers are increasing. 060. Now we're turning east. So as we turn left, you can see here what the pilot sees down there, hitting 030, and now we're going up to north, true north. I suppose they just look at that and digest it and slowly get their little brains around it. So, errors. So the first one's an acceleration error due to the dip we talked about. What was dip, Bronx? Have you been listening? So when we accelerate or decelerate, the compass is actually going to show a turn, or more specifically a change in heading, even though it's not happening. And this is due to the fact that we had to compensate for dip by having more weight at one end of the compass, or suspending it. The heading, the error, acceleration error, is greatest on east or west headings and non-existent on north and south, and in between to a greater or lesser degree. Let's have a bit more of a look at how this works. So here we have, okay, here's the tail of the aeroplane down here, just out of the picture. The yellow dot, that'll get rid of that. No. The yellow dot is the pivot point. Okay, so here's our bar magnet, our compass, and it pivots, so it can line up with the flux lines. That's the yellow dot. The black and white there is the centre of gravity, slightly left of the yellow dot to compensate for dip. So let's have a look at what happens when we accelerate. So watching the compass, accelerating and decelerating. Let's do it again. When we accelerate, we're not changing heading, but it's an apparent turn. Is it an apparent turn to the north or the south? Let's have a look. Accelerating, apparent turn to the blocks. Which one of these blocks? So it's going to show an apparent turn either to the north or to the south. Tell me which one it is. So we're heading east. Which way does it appear we are turning? Might need to run that a couple of times just to get it to sink in there. Another way of doing it, which you might be having to scribble this or do revision on a whiteboard. Let's say that there's an offset pivot here. Where's the centre of gravity? That side of the pivot, eh? Okay, let's accelerate. What's going to happen? Swing from there to there. Okay, let's decelerate. It's not marked, it's not a huge error in small aircraft because our rate of acceleration ain't that great. It's probably quite a lot in a high performance jet or something. But it is very noticeable if we, and we will, when we do the lesson, show you in the aeroplane this happening. So let's try it on east and west. What was the last slide? That was on west. Now we're on east, okay? Same thing. Now let's look at it on north-south. You'll notice that the centre of gravity and the pivot point are lined up in our direction of travel. So the centre of gravity is not offset from the pivot point this time. No error. Someone's put a heap of time into these animations, eh? Mm. Okay, how do we remember this? Easy. So if we're on headings other than north and south, especially east and west, if we accelerate, we'll get an apparent turn to the south. If we decelerate, we'll get an apparent turn to the north. Sand. So that's acceleration error. The next one is compass error. And there's a couple of bits to it. Turning error. So, because of the magnetic dip, you're going to get an apparent turn, not a real turn, when you tilt the compass. And it is due to, remember that picture earlier, we could only use the horizontal component but because of the vertical component of the Earth's magnetic field, we're going to get this error. Do you guys just, by the by, do you understand how this works? From your systems or whatever?
More or less.
Kind of. Yeah. Is that consensus? Could you explain it to me? Anyone? No?
That was feeling that brief.
It's a bit tricky, eh? Often, you'll be told that it's due to the vertical component of the Earth's magnetic field. Vertical component of the dip, and it's left at that, and you just move on. Okay, it's caused by the dip angle, and we know that there's an error when we turn. But to understand it, someone made this, and I only pulled it out of the cupboard yesterday and had a look at it because I've never used it before. Can someone talk me through how to use it or not? No? Okay. I'm winging it here. You might need to come out. What we do is we can set up we need a door handle or something to tie onto. Or we just go like this. Yeah, that'll do, eh? Have you seen this before?
No.
No.
Okay, come up here. That, because we can't see it, is a flux line. So imagine, which way would north be, that end or that end? At our latitude. Yeah. So there's north up there. Okay, so there's a line on here for north-south. You can see that, north there. So if we were flying north, how are we going to visualise that? Doesn't really work for me for holding it, so we're going to say it's a Cessna. And just like our PowerPoint, big compass, little aeroplane. So where are you sitting, Blocks? Which bit are you looking at? Oh, so I better turn it around like that because it's a direct reading compass, eh? So you're looking at the north on your compass, if you were flying like that. Yeah? So can you imagine the flux lines? There's the horizontal component and the vertical component. Okay, so let's, and of course, it wants to do that, so where's the weight? Yeah, to make it sit like that, right? Okay, so come a bit closer. So we're flying up to the north there. We're going to roll the aeroplane because that's what we do to turn, right? Roll the aeroplane. Let's take an extreme. We're through 90 degrees of roll here. Okay. So is our magnet between the fingers here, is it lined up with the flux line anymore?
No.
What do I need to do? is our parent 10. Yeah. Okay, so what does it say now?
0, 3, 0.
So it's about 30 degrees off. Okay. Let's oh, hang on, we'll just set it up again. And we'll go on a bit of a easterly heading. Okay. Right, so now I'm going to, I'm going to try and turn right, so I need to roll to the right. Okay. Is the flux line still lined up? Yeah. Vertical horizontal components have changed, but we're still lined up. What about something intermediate? I don't know. Let's say we're on a heading of, I don't know, 120. Where's 120? Well, there's 90, so 30 degrees off that. 9. Yeah. 3, 6. North. That's going east. Yeah, okay. Here we go. It says 06. What am I doing wrong here? It's 06. I put it up the wrong way. Here we go. 120. Like I said, I haven't used this before. Okay, so you can see our compass is still lined up with the flux line there. And when we roll, okay, is it lined up still perfectly? You might have to come a lot closer. How much off? 10 degrees? Yeah. So you might need to do a few of them. Everyone's got their head around that. Take it to the extreme though. You know, line up 90 degrees angle of bank. Shit, it's about 30 off. If I line it up, I can see it's 30 off. So it follows that a lesser angle of bank, it's still going to be there, isn't it? It's still going to have the error. So that's our turning error. There's actually more to it than that, but you know how we tell half the story of P of S? Right. Now it's important that these students get it in their head these errors. So what we want them to do is to memorise the compass. So you imagine that you're God looking down on stuff, looking down on the, you know, on the, like we're looking down on the top of the compass here, or this view. Looking at the big compass, you could be quite a way up. What are we looking at? So, first of all, we can go, give me the numbers, student can give you the numbers, call them out for me.
180.
180.
Okay, we're going to do it in 30-degree increments. Okay, so this will be 210, this will be
300. 120. 150. 030.
Okay, so vlogs will become very, very familiar with this. You need to have it memorised, you need to have a mental picture. So there's a line here running west to east. So we're over the line and we're under the line. Okay. Do you remember when we did this? How much error was there on when we did north and south? How much was it out by? 30 degrees? Yeah. Okay, what about on east and west? What was it? It was lined up perfectly, eh? So what do you reckon? What do you reckon it would be here? 2/3 of the way to 30, what's that?
21.
And this is easy, eh? So that's the headings we're going to work with. Over the line, under the line. Pretty easy to memorise that, eh? When you see how it's constructed. And this is how we, I missed a bullet point. And this is how we remember how to do this compass stance. We have to compensate for the turning error. How much do we compensate by? Well, we're going to overturn by 30 degrees if we're trying to fly onto north. We're going to underturn by 10 degrees if we're trying to turn onto 120. So get this committed to memory. ONUS, that stands for overturn north, underturn south. Easy peasy to remember. Over the line, under the line. Overturn, underturn. So how does this look? Okay, we're starting on a heading of north. Run the animation. What's the error going to be? 30. So have a look at the animation on the bottom right there. It's not matching up, is it? It's not matching up here, and there we go. Let's roll out when we get to, what's it going to do? I don't even know. West. No, we're going to keep going. You might need to get some familiarity before you do the briefing. You can see the turning error there. Look what happens when the aeroplane's on 150, which is now, the compass says about 130. When the aeroplane comes up to 180, what's the compass say? 150. There's your error. We saw that error, then that error, getting bigger. It'll get smaller now. This should be a 10-degree error. Yep. How much error coming up on west?
0.
Spot on. So that's how the compass behaves when we're in a right one turn. What's it gonna do here? Well, it's short of it, isn't it? For 30. Well, once you stop turning, no more error because it's turning error and we're not turning. So north is north. And just to reinforce the learning, there's a few things to note here probably. Let's have a look at what happens when we roll into the turn. So, we're doing a rate 1 turn, look at the compass down the bottom right, what's it doing? Very quick, isn't it? A very quick heading change. Jump out to the side 30 degrees almost instantly. And talk about whatever you want here, I suppose. Ask the students some questions. How much is the error? And when it comes round, I'm not sure, but I think it's probably going to roll out on 210. I'm hoping. That's what I'd like it to do. Not 210. 330. So we're just going to do when the compass gets to north, we're not going to roll out because we need to overturn. So there we are, through north, overturn by 30 degrees, looking at the compass, we've gone past north by 30 degrees, roll out, pick our reference point, make sure we're going straight towards it with the compass, it'll settle down and read correctly. So that's how we do it, management. Rate 1 or slightly less will work, anything more than that, these numbers will be different. And we don't go there. And the reason we don't go there is all of our instrument flying stuff we do, particularly towards instrument rating, is based on rate 1 turns. We talk about the deviation card, the compass card. If we haven't already, need to check it in the pre-flight when you look in the cockpit, blah blah blah. That could be a question, couldn't it? What do we need to check in the pre-flight with our compass? The student should know. And then you can add in the extra bits and pieces. Maybe tell a bullshit story about how mariners knew that compass was dampened with alcohol, and if they ran out of rum, they'd sometimes drink the compass and then get lost, or something. And taxi checks. Yeah, you're already familiar with them. So what are we looking for, blocks? Good chance to check on a bit of understanding that the aeroplane is turning around the compass. So when we turn right, the numbers increase or decrease?
Increase.
Yeah, so blocks can demonstrate that little bit of understanding. So we need a mental picture of the map, the world that we're flying in, and we also need to commit this to memory. So we can visualise this, we can visualise where North north-south is, and we can visualise the direct reading compass being direct reading and the way it operates. So we're going to tell you a bit about the procedure in a minute. Practice is the key, and there's three ways you can practice. You can practice in the aeroplane, that costs lots of money. You can practice in the simulator, that's a bit cheaper. Or you can just practice doing the maths and figuring out what heading to roll out on. And we're going to do a bit of that in a minute. We're not going to go near the aeroplane until you can actually do this, theory-wise. And what's the threat if we're looking in the cockpit a lot, focusing on some task like a compass turn and all the maths associated with it? So reinforce the need to be looking at. Okay, so we go through a sequence. I would probably, what comes next? Is there a slide after that? Sorry. Okay, I'm going to play this one. There's two ways you could do it. You could have that slide up there, which would work quite well, and then here you'd write about this. I won't do it actually. And then we could have which way do we turn, or old heading, new heading, which way do we turn, under rover, and do some examples. Or you could leave that one up there, in which case you have to leave this one up here. Okay? So, these are the way. You could do a table, and it would go like this. I've got chairs in the way, I'm not going to move them. Something like that, write it out in full, move the chairs so you're not tripping over them. Start with easy ones. Okay, we're going to turn left or right. What's the quickest way around? And this is where students can get a bit stuffed up, because they need to imagine the aeroplane here going north, and then the aeroplane will turn to the right until it's heading 120. So get the model and put it there, all there, make sure that understanding's there. And then of course Blogs is going to work it out. Okay, so we said right, under or over. Well, 120 is down the bottom. What's the correction? Help them with the first one. And what are we going to roll out on?
117.
Yeah. So other scenarios to give them. Okay, let's do another one. We're on 300. I want you to go on to 240, which I haven't written there. It's going to be a left turn under or over. It's going to be under by how much? 10, so that's going to be 230, right?
250.
Mm.
250.
Yeah, but 240 under, so minus 10 is 230. Yep. That's what students will do. They'll associate under and they'll subtract to come up with the answer. So that's when the mental picture comes in again. If we're turning left to 240 and we're under turning, we're going to stop short of 240. We're going to roll out 10 degrees beforehand. It's nothing to do with the maths. So make sure you throw in one of those examples and cover that one. What else can I tell you? Let's just note something here. So we're on 180, I want to go to 150, left or right? Turn
Left.
left, under or over, by how much? 20? Yeah. So if I stop short of 150, what's 20 this side of it?
0.
Yeah. So it's, you know, it sort of seems like it's only 10 degrees off. So that's only 10 degrees off. But we're actually changing by 30, and that's because the air is maximum on the sound. When you know, you can do quite a few of these, and then do the intermediate ones. Well, that's easy enough. 15 degrees. That's for the sharp students. I'd never ask them that in a PPL. Maybe a CPL I would. But not if they're struggling. And then, at some point, I'd be saying, look, this has got to be committed to memory. You need to be able to do this without that slide and without this. So I'm going to, before we go flying or swimming, I'm going to say, okay, you're on 120. I want you to roll out on the heading of whatever. Left or right, what do we roll out on? And just give them practice like that. Maybe give them homework. And if it's in the aeroplane, I'll say, we ain't going flying unless you can hit me back with the maths double quick time, because otherwise we're wasting our money. But where's the best place to teach it? Hmm? Yeah. Yep. What else can we talk about? No, I'm not going to complicate things with that. But just be aware there's more to the turning error because of there's actually another acceleration error due to the change in heading that is still going to be present in a flat turn like in a boat, but we're not going to go there. We'll just stick with you may hear of it or read about it, that's all. That's some shit they don't really need. Happy? Questions?
How long would you say this would take as the time at the beginning if you were to say
this is going to take such and such.
We've been here an hour if you include going to the toilet, making coffee, finding that thing. You don't want to do it too quickly, but maybe you do it in 2 bits. You give them the brief, little bit of this. Then they've got some work to do. Commit that to memory. Do the homework you gave them, and then there's quite a bit of checking on that learning prior to flight. They don't have to learn this, commit this to memory within the brief. They can go away and do that. So maybe, I don't know, 45 minutes. Depends how much you want to repeat the animations and talk about them, I suppose.
How switched on they are.
I think it's a really good briefing. Yeah.